So today we're going to talk about the police chase problem. In the police chase problem, as is traditionally thought about, there's a police car here, and in this case, he's just cruising along, minding his own business. Put some lights on top, a little blue light. A red light. So here's a police car. He's moving that direction. And at some point, some speedy car goes flying past him. In this case, though, to make it easy, I made it a motorcycle. So let's draw a motorcycle. So here's one wheel. Here's another wheel of the motorcycle. Okay. It's got some body frame. It's got some handlebars. And we got a rider on top. There's helmet. And he goes cruising past. So, the way the problem is set up is that the motorcycle has a constant speed. In this case, the motorcycle has a constant speed of 24 meters per second. And so we got to say the motorcycle is moving this way at a constant speed, the motorcycle of 24 meters per second. Where the police car has an acceleration, he has an initial velocity equal to 8 meters per second, and he has an acceleration of 4 meters per second So this is the initial setup for the problem. And what we're going to see here is that if the motorcycle is moving so much faster, he's going to pass, but because the police car is speeding up, he's going to be able to catch up. And the first question is, how far has the police car traveled when it catches up to the motorcycle? Well, this is a classic style problem because it is a accelerating object versus a constant speed object. And each of them will have its own mathematical model, its own mathematical relationship to describe its motion. So let's work with the police car first. So if I want to find the position of the police car at any moment, I know it obeys the constant acceleration equation, 1/2 at squared plus v0t plus the initial position. So that's the constant acceleration equation for an accelerating object. For the motorcycle, we have something similar. We have the position of the motorcycle is equal to vt. This tells us it's a constant speed type formula, so we have a rate times time equals distance kind of thing. Oh, I forgot. Plus the initial position. These are actually the same equation, but because the acceleration is equal to 0, this term is not in this equation right here. So they are actually the same. This one just has a 0 acceleration. So what's nice about this problem is that in both of these, the x0, since they both start at this starting line here, right? They're both here when it starts. So x0 is equal to 0 for both of them. And when it catches up, the position of the police car has to be equal to the position of the motorcycle. And this is our condition for them being at the same place. So we're going to use this, set these two equations equal to each other, and solve for time. So what that means is that try that again. The v of the motorcycle times the time is equal to 1/2 at squared plus v0t for the motorcycle. And if I plug and chug this away, I know this is 24t is equal to 1/2 times 4t squared plus 8t. And when I go to solve for this, subtract AT from both sides, I end up with 16t is equal to 1/2 of 4 is 2, so I have 2t squared. Divide both sides by 2t, and t is equal to 8 seconds. So the motorcycle, or the policeman, is going to catch up to the motorcycle in 8 seconds. But that's actually not the question. The question is, how far has the police car traveled when it catches up to the motorcycle? And so then, what I can do is I say I'm going to take my 8 seconds and I'm going to plug it back into the position equation to see where it went. So the position of the police car is equal to 1/2 AT squared plus V0t plus x0. When I plug in the stuff that I know, 4 is the acceleration, the time is 8 seconds, the initial velocity is 8 times the time is 8 seconds, plus the initial position, which is 0, that's the starting line. It'll allow me to know how far it went. I can do the quick mathematics and work it out. 8 squared is 64, half of 64 is 32, 32 times 4 is 128, plus 8 times 8 is 64. So the position of the police car is equal to 192 meters. Now, that's a good answer, and that's a fine answer. Actually, what's interesting about this is we could have gotten to the answer a little more simply, because the police car was lagging behind and eventually caught up to the motorcycle. So what we could actually suggest is that if we found the position of the motorcycle as given by its velocity times the time, the position of the motorcycle would be equal to its 24 meters per second times 8 seconds. The position of the motorcycle was also equal to 192 meters. And so it's not surprising that they both ended up traveling the same distance and had the same position, because that was the condition for the problem, was it had to catch up. The second part of the problem says, how fast is each moving when it catches up? No problem, we can easily solve for that. So in this case, we're going to say, well, how fast is each moving? Well, what are the velocity situations? The velocity situations are actually pretty easy. When I think about the motorcycle, for example, the velocity of the motorcycle is equal to 24 meters per second and is constant. So how fast is the motorcycle moving when the cop car catches up to him? The answer is 24 meters per second, because it's constant the whole time. The velocity of the police car, however, is determined by AT plus V0, where A is the acceleration, T is the time, and V is the initial velocity. But we know all these things. It was given to us that the acceleration is 4. We know from our previous problem that the cop car catches up in 8 seconds, and the initial velocity was also 8. Do a little math on that one. 4 times 8 is 32, plus another 8 is 40 meters per second. Now, it's interesting to me to consider this, is that the motorcycle is moving at 24 meters per second, so to catch up, it obviously had to be going faster for a good deal of time. And in fact, we can see that it is 16 meters per second faster. And I find that interesting because if the initial velocity was 8, it looks like he's 16 meters per second slower when it starts, and then 16 meters per second faster when it catches up, and I doubt that is a coincidence. The next part of the problem asks, how far has each traveled when they're at the same speed? All right, well, let's get rid of this and start again. So this question doesn't ask when they're at the same place, but asks when they're actually at the same speed. So let's see if we can figure that out. Well, we know, again, that the velocity of the motorcycle is 24 meters per second and constant. no big deal. We also know that the velocity of the police car is given by the equation AT plus V0, where the acceleration is 4 and the initial velocity is 8. And we want to know what happens when they have the same speed. So when is the V of the motorcycle equal to the V of the police car? Now, because these are both moving in the same direction, in this case, the velocity of the motorcycle and the velocity of the police car is the same as the speed of the motorcycle and the speed of the police car because they never have opposite velocities. So we can use this as our condition. And if I set these two things equal to each other, I end up with 4t plus 8 is equal to the 24. Subtract 8 from both sides, and I end up with 4t is equal to 16. So t is equal to 4 seconds. So we know that it catches up, or that they have the same speed 4 seconds after he gets past. But the question is, how far has each traveled? No problem. When I think about the motorcycle, is the position of the motorcycle is equal to the velocity times the time plus the initial position of the motorcycle. Well, this is no problem for us. The velocity is 24, the time is 4 seconds, and its initial position was 0 because they both start at the starting line. And so the final position, 4 times 24, is 96 meters. And so since it started at 0 and it ended at 96, the motorcycle went 96 meters. The police car, however, we know that's determined by 1/2 AT squared plus V0t plus x0. When I put in everything I know here, 1/2, the acceleration is 4, the time is 4 squared, plus the initial velocity was 8, again the time is 4, plus the initial position was 0 because it started at the starting line. The position of the car, 4 squared is 16, half of 16 is 8 times 4 is 32, plus 8 times 4 is 32, and so the final position is 64 meters for the car, the police car. So in the time, right, the motorcycle's traveled 96, the police car's traveled 64, and what that means is it's still behind. That's not that big of a deal because he's accelerating, the police car is accelerating, so we'll still have time to catch up. But what we'll notice is that this 4 seconds is half. So I think that might be interesting moving forward. So the question was, how far did each go? This one 96, this one 64. The last question is kind of a hard one. It says, what is the maximum separation between the police car and the motorcycle? Well, I think the real question is, when does the maximum separation occur? And the answer is, the max separation occurs at t is equal to 4 seconds. Why does the maximum separation occur at t equals 4 seconds? Well, before 4 seconds, the speed of the motorcycle was greater than the speed of the police car, which means he was still pulling away, increasing that. But after 4 seconds, the speed of the motorcycle is now less than the speed of the police car, which means the speed of the police car is greater, which means he is now narrowing the distance, so he's getting closer and closer. What's nice, though, is that because of the previous problem, we actually have the two distances at 4 seconds, so if the maximum separation occurs at 4 seconds, we can just subtract. So the separation is equal to the position of the motorcycle minus the position of the police car. So we have 96 minus 64 equals 32 meters, and that is the maximum separation.